Bienvenue, bonjour, welcome. Merci d'être venu. So, BCS. So we'll start from where we were supposed to be last time. I will discuss broken symmetry from the point of view of effective medium theory that we have described already, and about phase coherence and the Eliashberg equation. Then I will discuss the pair wave function. What does it look like? And find the expression for TC, and most importantly, the expression for the ratio between delta and TC. That's or KBTC. That's a very famous result from Bcs theory, which works with many materials, but not all of them. And Eliashberg takes care of that. And I'll show you how we can get different pair wave function depending on the structure of the interaction parameter. So where are we? So I remind you that in the ferromagnet, we were studying Sz at Q equals 0 as a function of tau, and Sz Q equals 0, 0. And the integral of this from 0 to beta d tau is just a susceptibility. And the spin susceptibility for Q equals 0 diverged in the normal state. And then in the ferromagnetic state, we decided, we showed that the expectation value of Sz at Q equals 0, well, it's time independent and it's non-vanishing, whereas in the paramagnetic state, it is vanishing. Okay, so for superconductivity, what we did is the analog of this. So we started from the normal state, and we said, okay, let's look at the psi dagger up, psi dagger down at Q equals 0 as a function of time. And same thing here, psi down, psi up. Okay, so that can be non-zero in the normal state because it conserves the number of particles. Now, we said that this diverges, but to be able to see that, we used again this formalism, but now we did a canonical transformation that took us to this strange spinners that are a combination of destruction and creation operators, but they obey the correct canonical commutation relation, and the Green's function then has off-diagonal components. And the reason it's useful is that if you look at this, for example, or this one instead, if you here I assume translational invariance, but if you don't assume translational invariance, this is precisely this product psi dagger, and we want to see how it responds to an external field, psi, that couples to the parallel also. So the formalism was the same, except that when we go back to the actual Green's functions, then we have to realize that the down spins, they have to go, the arrow has to be in the opposite direction. Because in the Nambu notation, this is psi dagger, but if you go back to the original notation, then one of the two Green's function will be with C dagger C, so you have to put the arrows backwards. So what we did in some sense is just to sum all these diagrams, because we used this as an interaction, and we substitute, we take the functional derivative and we substitute here. Now the interaction V that comes in is just the usual interaction, except it will be attractive because of the retardation and when we saw with the phonons. When we write the density operator for some interaction. I mean, you have density here, and then some interaction potential. I need to put a tau 3 if I use the Nambu notation. Tau 3, I put the 3 on top here. Simply because, again, the operators are in the wrong order here. Okay. So with tau 3, then everything becomes fine. So we use this Hartree-Fock approximation. When we take the functional derivative, we go back here, and then it's like summing all these things. And again, we saw that it diverges. Okay, the susceptibility diverges. So in the same way that we had the expectation value of SZ equal to 0, now we have the expectation value of psi dagger, which is different from 0. Yeah, Q equals 0 again. Psi dagger, or psi. In other words, in the superconducting state, then we need this full matrix here. So we will proceed just like the ferromagnet. And we will say that we will take some trial Hamiltonian. So now K, that is H minus mu n, as some trial Hamiltonian K0 tilde that breaks the symmetry. And then we have plus H0 minus H plus V minus H0 tilde, sorry, H0 tilde. Operator. Okay. So what is this? What do we guess here? Remember, for the ferromagnet, we just guessed that all the spins were up. Now for this, what we will guess is that there are off-diagonal matrix element. So in other words, K0 tilde operator will be the sum, we assume translational invariance, so sum of our wave vector, and then we have a Nambu spinner, psi, that has two components, psi dagger, these two components, and then I will have, like in Hartree-Fock, I will have a psi k tilde, so that's epsilon k minus mu tilde, it needs to be determined. And now I need tau 3 here. Oh, tau 3, I always need tau 3 on top here. Right, because psi k. Again, because when I look at the component that is for downspins, the operators are in the wrong order. So when I put them back in the right order, there's this tau 3. And that generates a constant term, but constant terms don't do anything. Now, we also have these off-diagonal components, okay? So I will stay in the basis of Pauli matrices and write this as delta 1 tau 1 plus delta 2 tau 2. Well, tau 1 and tau 2 are the usual Pauli matrices, but they are now acting on Nambu space. So, well, it's not important to remember. Tau 1 is 0, 1, 1, 0, and this is 0 minus I 0. It's not, but the details are not important. We just know how polymatrices work. So, what is the Green's function for this now? Well, we know the structure of the Green's function. The Green's function G, given this, the Green's function tilde, if you want, the one that comes from K0, G minus 1 of K IKN will be equal to IKN minus what's here. So it is IKN times the identity minus zeta tilde K tau 3 minus delta 1 tau 1 minus delta 2 tau 2, and that's a function of K also. I have to be careful here. Okay. In general. Okay, I just do, and as soon as I have these non-Boole operators, it works exactly the same as before. And you can check that in a little bit more detail here by having, you know, this Green's function, when it goes back to the correct order, you get the plus sign, and then the tau that would become here in minus tau. So we get minus IKN, but we have changed the sign in front, so that's why we get IKN here. Okay. And now we just do what we did before. We decide that we have an effective medium. So we want the self-energy to be 0. So the self-energy of K IKN is equal to, so this H0 minus H0 tilde is like the counter term. So we have zeta K tau 3 minus zeta K tilde tau 3. And then this we treat in Hartree-Fock. Okay. So we have in Hartree-Fock, there's minus sign here. And so you have minus, and then, okay. Well, I can write below here. The diagram is this, right? So we come in with K. We go out with K. So here we can write, for example, K prime. And here what will we have? We will have V of K minus K prime. I don't need to worry about plus or minus because it's symmetric for the interaction potential. So let me write this. So I have the integral d cube K prime over 2 pi q. And then I have this, I have the tau 3. Because I have to not to forget that there's tau 3 here at the vertices. So I have V of K minus K prime, and then this Green's function is sandwiched between two tau 3. So I have tau 3 and G of K prime ik n. Here I have no frequency dependence in the V. I take the BCS model times tau 3. Okay, so before I can do anything, I need the Green's function here. But you see, I will put this equal to 0 in this effective medium, and that will give me an equation for psi k tilde. And oh, I forgot this. I mean, sorry. In the k0 tilde, there are these terms as well, right? I forgot them. So we have minus delta 1 tau 1 minus delta 2 tau 2, and these are function of k. Yes. Okay, and that will give me a self-consistency equation for delta 1, for psi delta 2, and psi tilde. But I need the Green's function. And the reason I use this Pauli matrix formalism is that it's easy to invert the Pauli matrices. So I'll show you the trick. Is that clear? So we have the H0 minus H0 tilde. So that's H0. That's the piece that's like the non-interacting piece. What we had, and then that's a broken symmetry Hamiltonian. Okay, and this is the R3 fuck term. So what is the Green's function? We will use an identity that is that A times the identity matrix minus some vector dotted into the 3 Pauli matrices times A times the identity plus vector B. I have to change color all the time because the pen are dying. Plus B times tau 3. I'm sorry. This is equal to A square minus B square times the identity. Okay, you have to realize that this is a matrix, right? That's A times the identity matrix in 2 by 2 space. And B dot tau, it just means that I have, just like here, the vector B here would have component 3 that is psi tilde, and the component 1 that's delta k, and it's okay. So this is just a shorthand for what is here. Okay, but the B is like this. Now, why is that true, this identity? Well, clearly the cross term here, A times this identity minus this, that cancels, okay? And now this times this is A square times the identity, so that's fine. So I need to show now what happens with this B dot tau square. So suppose that, let me take just one component, okay? Two components. So let's take B1 tau 1 plus B2 tau 2. Okay, and now I multiply by B1 tau 1 plus B2 tau 2. Okay. So if I look at the square of a Pauli matrix is the identity. Okay. So that's B1 square. So, and that's B2 square. And I add a minus sign here. So that gives this. Now what happens to the cross terms? If I look at B1, B2, B1, B2, you see that I have tau 2, tau 1, plus the other side, right? Plus tau, the other order, tau 1, tau 2. And Pauli matrices anti-commute. Okay? So we have inverted these, we invert this Green's function in a very cheap way. We have that G of K IKN is just equal to the identity times IKN, and then this becomes plus zeta tilde K tau 3 plus delta 1 tau 1 K delta 2 K tau 2. And remember that so in other words, I multiplied the numerator and the denominator by this matrix, if you want. And so, or if, well, okay, let's take G minus 1 and multiply by this. What will happen? This will not give me the identity, but we know that G times G minus 1 is the identity. So I need to divide by zeta tilde K square plus delta K 1 square plus delta K 2 square plus I K M square, and here I have a minus sign. Okay, so if I multiply this by this, I get the denominator, so it cancels. Now you know that the poles of the Green's function will be the one-body eigen energies. So this, let me call this, and that will come back all the time. Let me call this E of K. Okay, are you going to be sad? I'm going to erase this, finally. I don't know if I'm able because it's been there forever. So the last class will be on Friday. On Monday, I will give another class, I think, but this will be just if you're interested. I will complete this formalism in the sense that to show you that the self-energy itself, okay, this vertex is a functional derivative. The self-energy is a functional derivative as well. So I'll show you this. This is called the Luttinger-Ward functional. And from that, I can derive also the dynamical mean field equations. So I will define E square of K as zeta K tilde square plus delta 1 square plus delta 2 k square. Okay, so so let's see now what this looks like. Okay, you see there would be with R3 fuck we just had that psi tilde was psi k minus u times m down. So this will be modified because now we have something else. But superconductivity occurs at relatively low temperature, and so the modifications will not be very large for this the psi k tilde. So I'm more interested in what happens to these off-diagonal pieces, right? So I will need G is equal to IKN I plus psi k tilde tau 3. And you will see in the end, I just need one or the other. So for now, let me just write delta 1 k square. In fact, I won't need 1 anymore, divided by IKN square minus EK square. So this is 0. Let's look at the off-diagonal component. The Pauli matrices are an orthogonal set of a basis for the 2x2 matrices, right? So the coefficient of tau 3, the coefficients of tau 3 have to be equal, and the coefficients of tau 1 have to be equal, and the coefficients of tau 2 have to be equal. So here, I get that delta, and you see that given this, here it has delta 1 square plus delta 2 square. So given this shape, you see that the equations for delta 1 and delta 2 would be identical. So I need only one of them. So I take delta k, I will drop the 1, is equal, I put this on the other side, so is equal to, well, this one on the other side, is equal to minus this. But now I will look at the, here I forgot tau 1. So I will look just at the off-diagonal component. And tau 3 times tau 1 times tau 3 is equal to minus tau 1. Okay? Because multiply by tau 3 here, and you will get this. And we know that Pauli matrices anti-commute, so that's the right equality. So the minus sign drops out, and we are left with integral d cubed k over 2 pi cube. I will take pen. I will try to get pen with the same color next time. It's a little bit embarrassing. Times v of k minus k prime. And then I get this delta. There's no square here. It was delta 2. So times delta k divided by IKN square minus EK square. And here I always need to do the sum over Matsubara frequencies as well. So there's equal T times sum over IKM. Now I can easily do this. So I get, I can do it if I proceed like this. Sum over IKM. Well, let me work right away with this. Okay, you see what happens here? I put this on a common denominator. It gives me IKN squared minus CK squared. But the numerator, I have epsilon k minus epsilon k, so 2 epsilon k. So I need this because the Green's function was delta over this. So now I can do the sum over Matsubara frequencies, and I'm left with just this integral d cube k over 2 pi cube times v of k minus k prime divided by 2 ek prime. That's what I'm integrating over, right? It's g of k prime, so I need to put prime here. K prime. Delta of k prime. And here I get the Fermi function of E of k prime minus the Fermi function of minus E of k prime. So this is equal to the integral d cube k over 2 pi cube. And in the BCS, just for now, if I do the same that we did in the normal state, what I have here is just V. And here I have delta k prime over E k prime. And here I have f of E k prime. And f of minus E is 1 minus f of E. So it's minus 1 minus f of k prime. So all of this can be written like this. So I have delta k is equal to the 1 here, I will put the minus here, minus, and then I have 1 minus twice the Fermi function of a positive energy. Okay, I've defined Ek. Ek really is the square root of this, but I've taken the positive square root when I divided it like this. So this is 1 minus 2 f. So this is the famous BCS equation. Any question? As in, you have question? No?
No?
Okay. So let's continue. So one important thing here is to see a phase coherence, in the sense that remember that this delta is related to these off-diagonal components, and there's a phase here in these off-diagonal components. So if I keep this more general equation here I have assumed BCS, but if I keep, so I'm discussing this phase coherence here, delta K. Then there's a minus sign. And here, this I can write as hyperbolic tangent. Of beta EK over 2. And remember that EK is positive here all the time. Okay. So now I can multiply this by the square root. Let me define, this will be sort of a temporary definition, but let me define C of K is equal to hyperbolic tangent beta EK over 2 divided by 2 EK to the power 1/2. Okay, so this quantity it makes sense because the hyperbolic tangent E is positive, so I'm taking the square root of a positive number, and I take the positive value. So C of K is a positive number. So if I write now CK times delta K, so I just multiplied by CK. Then I have minus integral d cube K over 2 pi cube times CK V of K minus K prime. And this object here I can write as CK prime square. So I have CK prime times a CK prime delta delta of K prime. And V is negative here, so there's a solution. Okay, that's positive. I'm sorry, we don't know that yet. Okay, so what is this guy here? You can think of this as a matrix. Okay, and this integral over K prime, that I forgot my prime everywhere, K prime, K prime, K prime, sorry, it's so bad this today. So this is a matrix, but it's a real matrix and it's symmetric, okay? So a real symmetric matrix has real eigenvectors. In other words, this here cannot, the dependence on K prime cannot, at some point I cannot get a complex number here when I go down the K prime. But in general, the delta can be complex. So what does that mean? It means that there can be an overall phase, e to the I phi, that's allowed. I mean, you can add e to the I phi. But that phase here cannot depend on k or k prime. It's just a constant phase. So that's an important point. I mean, that's the superconductor is phase coherent. Okay, phase coherent here, that means that for all values of k prime, so you see delta here is related, is an off-diagonal component, so it's related to this object. And this delta here, the value of the phase cannot depend on the value of k prime. Now you could still have some dependence on a large length scale. You can imagine there's the wave function here. On a large length scale, there can be some dependence on the phase can vary slowly over space. So then it means that if you write a Landau theory, and that was done by the London brothers and by Landau before the discovery of Bcs superconductivity, is to postulate that there's h bar grad over I plus 2. I mean, the 2 they did not know at the time, but we know that there's a 2 E times the vector potential, everything square times psi times an A, and this is psi square A over 2 plus B over 4 psi 4. Okay, and we can write a Landau theory that looks like this near the phase transition. But now this psi, what is this psi? This psi is this object here that has 2 fermions. So that's why there's a 2 here in the coupling to the electromagnetic field. So this approach is very useful to know the effect of electromagnetic fields on superconductivity. So you get this way, you can get the Meissner effect, you can get the quantization of flux, you can get many things that are more difficult if you want to do it from the microscopic, including everything. So that's one thing I wanted to add. Now, what about Eliashberg theory? Well, Eliashberg is necessary to have a more quantitative theory. I will show you that there's a very famous ratio. I will proceed to do it now, actually. Very famous ratio for BCS theory. That is that 2 times the gap at t equals 0 divided by, if I put back the K Boltzmann times Tc is equal to 3.53. Now you find some superconductors that don't obey this equation, and Eliashberg theory takes care of them, but it's even much better than just fixing this number. So Eliashberg theory is in practice complicated to solve. I won't do that, but in principle is not very complicated. You just do exactly what I did here, but then you allow this gap. You allow this gap to be frequency dependent, IKN. And then the self-energy if I look, you assume that it has, well, you can show actually using various arguments that it only frequency dependent. So if it's frequency dependent, then the sigma of IKN, it has an odd and an even part. So if you look at the odd part, so sigma of minus IKN, and here it's just convention. It's just a matter of definitions. So if we look at the odd part, it is defined as IKN times 1 minus Z of IKN. In general, because of this K dependence here, it can depend on K, but here in the strict Eliashberg, it depends only on IKN. And then if I look at the even part, so this plus this divided by 2, by definition, you call it chi of IKN. So you have 3 unknown functions, delta of IKN, Z of IKN, and chi of IKN. 3 unknown functions. It's only 3 because these 2 are simply related by complex conjugation. So you have 3 functions, and you have the Pauli matrices tau 3, tau 1, tau 2. You get 3 equations out of that. And okay, the important piece is that this V here, you don't take the simple BCS model, but you take the actual phonon propagator, okay? So in this V, we'll have the Coulomb interaction, but the Coulomb interaction just within the window where there is attraction. We saw that attraction is limited to the bifrequency. So you sort of have an effective Coulomb interaction that is in the, you sort of integrate out all of the high energy processes, and that gives a much smaller Coulomb interaction, which in the end ends up just being described by an effective parameter that's called mu star. And this, then you get the real phonons here. So this is the phonon propagator, and that we wrote omega q square over omega square minus omega q square. But you can go beyond just this simple thing. And then what you find is that, okay, if you look at the phonon density of states, that there are peaks in the phonon density of states, okay? There's some frequency dependence. So the frequency dependence of the phonons will end up showing up in this delta. Okay, delta will become frequency dependent. And you can measure that by tunneling. And then you can see that the peaks in the phonon density of states show up in this. More than that, because the BCS equation that you see here is nonlinear, there are harmonics of these phonons. Okay, so it's very beautiful. You from tunneling, you can measure this delta as a function of frequency, and you see the peaks in the phonon density of states, and you see the higher order harmonics. So it's hard to make a better theory. Not only that, but this ratio that we will derive for BCS will be different for some superconductors, and this, you can explain that as well with the same theory. So what are the superconductors where you need to do all this, more sophisticated equation? These are so-called strong coupling superconductor. So when the electron-phonon interaction, here we just use the Jellium model, but in general, you have many bands, and you're just interested in bands and the Fermi level. So there are some electron-phonon interaction. So when the electron-phonon interaction is large, you need to do this. So if we had just BCS, perhaps we would have never been completely convinced of the formalism. But why? Because all the superconductors obey this. So when they, where are the phonons? Well, the phonons, they show up in the isotope effect. So the TC, the equation for TC that I will derive depends on the Debye frequency. If you change the isotope, you get a different Debye frequency, so you get a different TC. Okay, so that's a way to see that the phonons are involved. And the other way to show that the phonons are involved is this, that you see the structure of the phonons, and you can measure the phonon density of states by neutron scattering and check that the phonon density of states is shows up in this equation. And you get everything else to work out as well. Okay. So even though I will, I won't get into trying to solve the Eliashberg equation, within this framework, it's easy to understand where it comes from. Do you agree? Okay. So I'm running out of time again. Let me end. Okay, next time I'll derive this 2 delta over k BTC equals 3.53. Now, for now, let me just look at the Bcs wave function, the pair wave function, and just make a quick comment on that. So what is this? If I look at this at equal time, so I look at minus ck up, c minus k down. At equal time, it means I need to take this piece of the Green's function. I have the Green's function here. I have to take this piece and sum over all Matsubara frequency. Summing over all Matsubara frequencies put me in equal imaginary time, but that's the same as equal time. So I just do the sum, t times the sum over I kn of this octagonal piece that I can write as delta k over 2 ek times, just like I did here, 1 over ikn minus ek minus 1 over ikn plus ek. Okay, and then when I do the sum over ikn, I will just get, just as before, this will become 1 minus 2f of ek with a minus sign. Minus, and then I have 1 minus 2 f of ek. Okay, now you see that if, so the right-hand side here is completely independent of if I have inversion symmetry or time reversal symmetry, this ek is independent of the sign of k. E of k is equal to E of minus k, if you go back here. So the same for delta of k. So, well, in that case, it's an assumption. If I assume that delta of k is even in k, that would come out from here. Then you see that if I change k for minus k, this cannot change sign. So this is equal to minus c of minus k up, c of k down. But now if I know that if I start from here and I interchange the two fermions, this should be equal to plus C of minus K down, C of K up, right? Because I just exchanged two fermions, so it changes sign. So how can this be equal to that? Well, it's equal to that if it changes sign when I exchange the spins. Okay, and that means that the pair, the spin wave function has the structure up, down. I see up, down, and I write up, 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 down, minus, down, up. So it is a singlet in the spin channel. Okay, perhaps the last comment is that now this, I can take a Fourier transform and go back to space, right? And if I do that, you see that there will be an extent in real space. I take Fourier transform of this. So there's a size to that pair, and that's called the coherence length. The size of a Cooper pair will just be related to delta. So as K becomes large, this becomes negligible, so it goes down like 1 over zeta K. So in the end, this coherence length will be related to the Fermi velocity, the Fermi velocity and delta. Okay, so we will have that C0, the correlation length, will be V Fermi over delta. Okay, so it's late already, sorry. So we are in week 13. So next time next Friday, I'll try to finish a BCS theory as much as I can. And then on Monday, if you're interested, you come. If you're not interested, you don't come. I will just do some extra material with, as I say, I will show this Luttinger-Ward functional that can be used to derive the DMFT and sort of completes this formalism in the sense that sigma will also be a functional derivative of something that looks like the free energy. Okay, because I have not written anything for the free energy now in this formalism, but I will do that. Okay, any questions? Okay, so see you Friday then. If you have some questions, I will stop recording. If you have some questions, let me know. I will stick around.